It is said that a transistor is a transistor only after BIOS, because transistor is active device. It becomes active only after BIOS. BIOSing makes the transistor active. It also biases the transistor in the appropriate zone. For amplification, transistor requires to be in active mode. Not only that, a BIOS circuit places the operating point at an appropriate location and maintains it stable without the point being drifted. Several biasing circuits are available in use. At one end, there is fixed bias circuit. At the other end, self bias. In the middle, collector feedback bias, emitter feedback bias circuits are available. First one, fixed bias, is crude circuit, but it is simple. Last one, self bias, is considered to be highly versatile, but it is somewhat complex. Depending upon the necessity, one can select one biasing arrangement out of these four. The merit of these circuits, bias circuits, from stability point of view, they are measured, they are calculated with the help of three parameters: stabilization factor S, stability factor S prime, stability factor S double prime. These three parameters are able to give certain idea regarding the ability of a bias circuit in providing stability to the bias point. Electronic devices, biasing and stabilization. Series on semiconductor devices and circuits, lecture number 3.14. Biasing is a circuit technique by which one can obtain desired behavior or good performance from an electronic device like transistor or diode. This technique involves application of or connection of one or two DC voltage sources along with a resistive network to the electronic device. If we want amplification from BJT, we have to operate it in active mode. Emitter junction under forward bias, collector junction under reverse bias. These biases are provided by biasing circuit. Bias circuit is mainly meant for establishing the operating point at a proper location. Location of operating point has a heavy bearing on the efficiency of the device, the distortion generated by the device, and even has certain influence on the gain provided by the device. Hence, biasing circuit influences all these aspects in an indirect manner. Directly, biasing circuits They are capable of influencing the values of input impedance, output impedance, and through impedances, the gain of the device too. In addition, these indirect and direct influences, proper design of biasing circuit helps in providing stability. Stability of the location of the operating point. Biasing and stabilization, these two are inseparable aspects of BJT amplifiers. With this small introduction, now we move to begin the session, which is about different biasing circuits, their merits and demerits, along with their ability to provide stability to a BJT amplifier circuit. We begin the session with a few points regarding operating point. Operating point is also known as a quiescent point. Q is the symbol. It is a fixed point on the characteristics that define the region which will be employed for amplification of signal. So it is a point, fixed point on the characteristics that define the region which will be employed. Another way of understanding the operating point is, it is a point on the characteristics of the transistor identified with the currents and voltages that are carried by transistor. Biasing establishes this point for a transistor amplifier. As already mentioned, location of operating point influences the efficiency of the device, distortion generated in the device, and also even the gains, impedances, etc. So, proper location of operating point is the most significant aspect as far as amplifier design is concerned. Its location is determined by biasing circuit. So it is the biasing circuit which is critical in the operation of transistor amplifier. The selection of Q point depends on several factors. They are listed here. The AC and DC loads of the stage, available power supply, maximum transistor ratings, peak signal excursions to be handled by the stage, tolerable distortion. These are all the aspects the design engineer has to take into consideration. He has to keep all these things in his mind while designing the amplifier circuit, especially the biasing circuit. After having some understanding regarding operating point, now we move to biasing circuits. Biasing is an act of application of DC voltages to establish a fixed level of current and voltages. This level is called operating point. So to establish operating point in the transistor, biasing is used. It is a technique, circuit technique. In this technique, one or two DC voltage sources are used along with the resistive network. Several types are available. First one is fixed resistor bias. Second one is emitter feedback bias. Third one is collector feedback bias. Last one is voltage divider bias. It's also known as 4-resistor bias. Another name for it is self bias. One or two points before going further can be stated regarding these four types of biasing techniques. As we move from fixed resistor bias to voltage divider bias, we can notice certain increase in the complexity, more number of components one can find in the bias circuit. So complexity, a little bit of complexity increment is there as we move from fixed resistor bias to voltage divider bias. General statement. Another observation is the performance of the bias circuit also increases as we move from fixed resistor bias to voltage divider bias. In fact, most of the times voltage divider bias or self bias or 4-resistor bias is used. Very rarely fixed resistor bias is used. Except the last one, all the remaining three, they are associated with certain drawbacks. And the first one is associated with a serious drawback. Out of the four, last one is widely used for its stability. As already mentioned, the purpose of biasing circuit is not only to establish operating point at a proper location, it also requires to provide stability. Stability means prevention of the operating point drifting away from the place where it was located in the beginning by the design engineer. When bias point shifts or drifts, what happens is the behavior of the transistor changes. Performance of the amplifier circuit changes. Now things become unpredictable. A few points regarding fixed bias circuit. Here is shown fixed bias circuit. This is transistor, DC supply, voltage supply, RL is load, CB1, CB2. These are blocking capacitors or coupling capacitors. RC is collector resistance. Usually it is included in the circuit to provide certain amount of safety to the transistor against unexpected and high variations in VCC. VCC is supposed to be constant, but for one reason or other, VCC may vary. RC provides certain amount of protection against these variations. This protection is for the transistor. Now RB is a resistor. Notice this is the amplifier circuit, so emitter has to be biased in forward direction, collector has to be biased in collector junction, has to be biased under reverse bias. If we go in a crude manner, these two junctions require two DC voltage sources for their biasing, but a careful design, a design with wisdom, it makes us to bias, to provide bias for both the junctions with a single source. Now a few points regarding the circuit. This bias circuit is also known as base bias, and also it is known as fixed current bias. It suffers with a disadvantage. It is the dependence of collector current on DC current gain, implying shift of bias point when there is a change in the temperature or during replacement of the transistor, and also the uncertainty associated with the bias point. So, two disadvantages. One disadvantage is shift of bias point whenever there is a change in temperature or whenever there is replacement of transistor. Another disadvantage is uncertainty associated with the bias point. Unpredictability is another disadvantage. Another feedback circuit is shown here. Name is emitter feedback bias circuit. The circuit is shown here. CB1, CB2, I have already explained the purpose of these two capacitors, RC, VCC. These are all known to us. RL, this is transistor. Now, what is new in this circuit when compared to the previous one, base bias circuit? New is existence of a resistor in emitter terminal, RE. RE is added. Notice RE is meant for providing stability. As RC is to provide safety, RE is to provide stability. RB is to be able to provide reverse bias to collector junction, forward bias to emitter junction using a single source. Now, a few points regarding the circuit. The emitter resistor provides a local feedback and stabilizes the bias point of the transistor in the face of variation in DC current gain of the transistor. Another circuit, collector feedback bias circuit. The difference between this circuit and the previous circuit is RB. RB's connection points. One end of RB is connected to base, other end is connected to collector terminal. Some points regarding this circuit. This circuit has an improved bias stability when compared to base bias in the face of variations in DC current gain. See, this term DC current gain is coming repeatedly in all the three bias circuits. So far we discussed what is this DC current gain. It can be beta or it can be alpha also, but usually beta is provided by the manufacturers in the data sheet that comes along with the transistor. This beta depends upon temperature. When temperature varies, beta varies. When beta varies, current varies. Current varies. What is beta? Current gain. Current gain is output current by input current. When beta varies, naturally, output current varies. When output current varies, bias point, it shifts or it drifts. That's what he's telling. This circuit has an improved bias stability. Major advantage is the feedback from collector prevents the transistor from going into saturation. This point. Earlier this point is here, now it is here. The emitter resistor is not compulsory, but when present it improves the bias stability further. So notice RE is always for stability. The purpose of RE, emitter resistor, is stability. Now fourth one, self-bias circuit. As already mentioned in the beginning, this is most versatile, widely used and highly useful in providing stability. So notice RC is there, RE is there. The purpose of RC and RE, they are already explained. R1, R2, these are bias resistors, R1 and R2. Earlier only one resistor was there, it was called RB. But here two resistors, R1, R2. VCC is bias voltage source, RL is load. A few points regarding circuit. It is also known as voltage divider bias or 4 resistor bias. This is by far the best biasing circuit for BJTs, which is almost completely immune to variations in the transistor DC current gain. The bias current collector current is almost completely independent of current gain. So notice operating point means IC, VCE. IC is output current. Temperature variations cause beta to change, resulting in changes in IC. But this circuit is able to prevent, arrest the changes in values of IC when temperature changes. Therefore, operating point is prevented from drifting. Prevention from drifting means providing stability. Now, a few points regarding bias stability. Bias instability refers to drifting of operating point from its designated location. It leads to unwanted, unexpected, and unknown. Unknown means unpredictable behavior of the transistor or circuit. This instability is mainly due to variation of beta from transistor to transistor. Here the point is, no two transistors can have same beta value. Even when these two transistors are made simultaneously, may be in the same batch of manufacturing, may be made at the same time by the same company. Even in those cases also, two transistors cannot have same beta. So, let us suppose there is a circuit, amplifier circuit. Inside, let us say there is a transistor, and for one reason or other reason, it got damaged. And when we replace this transistor with another transistor, then what happens is, the replaced one may have a different value of beta from the beta of the replaced one, which was removed. So beta differs. When beta differs, entire design changes. If we don't change the design accordingly, then what happens is different beta value naturally gives rise to different IC. Different IC means different operating point. Earlier operating point may be here, now operating point will be somewhere else. So variation of beta from transistor to transistor is one aspect. Another aspect is increase in IC with increase in the temperature. IC depends upon beta. IC depends upon IC naught, reverse saturation current at collector junction. Reverse saturation current doubles for every 10-degree rise in temperature. So IC naught doubles. When IC naught doubles, naturally IC also changes. Beta changes with temperature, resulting in change in IC too. So IC changes with the temperature. When IC changes, drift in operating point location automatically occurs. Now, a few points regarding stabilization and compensation. What is stabilization? What is compensation? BJTs, bipolar junction transistors, they suffer with one serious disadvantage. Technical name for this problem is instability. What is this instability? We want the operating point located at a particular place. But after design, when the transistor is put to use, initially for a few seconds or milliseconds, the operating point may be there where it is supposed to be, but then it starts drifting, it starts moving away from that point. This drifting away by the operating point from its designated location. It is called instability. Instability leads to performance deterioration and also performance unpredictability. So it has to be reduced. If possible, it has to be eliminated completely. Instability has to be removed from the circuit. Certain techniques got developed. These techniques which help us to arrest instability, to reduce instability. These techniques are grouped into two categories. One group is called stabilization techniques, another group is called compensation techniques. What are stabilization techniques? Use resistive biasing circuits. Stabilization techniques use resistive biasing circuits to reduce instability or to eliminate instability. They use resistive biasing circuits which allow to vary IB so as to keep IC relatively constant with variations in IC naught beta VBE. This is VBE. IC depends on IB2. IB is input current, IC is output current, DC. Of course, both are DCs. IC depends upon IB2. IC depends upon ICO, beta, VBE. So these resistive biasing circuits, they allow IB to vary so that IC is relatively constant even when it is forced to change by variations in IC naught, beta and VBE. And what are compensation techniques? They use temperature sensitive devices. Notice the difference between stabilization techniques and compensation techniques. Stabilization techniques, they use resistive circuits, whereas compensation techniques use temperature sensitive devices like diodes, transistors, thermistors, etc. to keep IC relatively constant with variations in IC naught, beta and VBE. This is VBE. A few points regarding stability factors. What are stability factors? They provide information whether the circuit is stable or not. If the circuit is unstable, they provide a measure of the amount of instability. Their expressions also give information regarding how to improve the stability. For general understanding, one or 2 points regarding stability factors. These are 3 in number: S, S prime, S double prime. These are the symbols. By finding S, S prime, S double prime, it is possible to estimate the stability or instability that is in the amplifier circuit. They give indication. They provide us information. Here he is telling they provide information whether the circuit is stable or not. If the circuit is unstable, they provide a measure of the amount of instability. Their expressions also give information regarding how to improve the stability. So they are useful. Here definition of these 3 stability factors are given. First one is stabilization factor S. It is rate of change of collector current IC with respect to IC naught, reverse saturation current, keeping beta VBE constant. Notice when it comes to stability, most of the times we are encountering IC. Why IC? Why not IE or IB? Reason is operating point means IC VCE. This combination is operating point. VCA, it doesn't change much, but IC varies. So it is the IC which causes drift in the operating point, which is the main culprit in spoiling the stability of the circuit. So IC is an important quantity when we are dealing with stability. That's why IC most of the times, while in the discussion about stability, we are encountering IC. So mathematical form of the definition is dou IC by dou IC naught, or delta IC by delta IC naught. Small change in IC by small change in IC naught. Stability factor S prime, it is the rate of change of collector current IC with respect to VBE, keeping IC naught beta constant. Mathematically, S prime is dou IC by dou VBE, delta IC by delta VBE. Small change in IC by small change in VBE. Third one, stability factor S double prime. It is by definition the rate of change of collector current, again with respect to beta, while keeping IC naught VBE constant. S double prime is dou IC by dou beta, delta IC by delta beta. Small change in IC by small change in beta. It is IC2 by IC1, beta 2 minus beta 1. What is this IC2, IC1? Small change in IC means collector current change from one value to another value. The first value can be IC1, second value can be IC2. The corresponding beta values are beta 1 and beta 2. Now, a few interesting and useful transistor parameters. IC naught for silicon transistor is 1.95 into 10 power minus 3 nanoamperes. For germanium, 1.95 into 10 power 3 microamperes. Microamperes. So therefore, for germanium, IC naught is more. This is at minus 65 degrees centigrade. At 25, it is 1 nanoampere for silicon, 1 microampere for germanium. Even at 25, 25 means room temperature. At 175 silicon, 75 germanium. It is 33,000 nanoamperes for silicon, 32 microamperes for germanium. It means for germanium at 75 degree centigrade, IC naught is 32 microamperes. For silicon at 175 degree centigrade, IC naught is 33,000 nanoamperes. Similarly, beta. For silicon, it is 25, 20, 55, 55. It is 100, 90. One thing to be kept in mind is beta is more for silicon when compared to germanium at any temperature. This is one aspect. Of course, at 25, both are equal. Otherwise, it is more. Another aspect to be kept in mind is it is varying with the temperature 25 to 55, 55 to 100. In case of germanium, 20 to 55, 55 to 90. IC naught also, it is varying with temperature. This is an aspect one has to be kept in mind. Similarly, VBE. For silicon, germanium, it is 0.78 volts, 0.38 volts at minus 65, 0.60 volts, 0.20 volts for temperatures 25, and at 175, 75. 175 for silicon, 75 for germanium, it is 0.225 volts, 0.10 volts. These values one has to be aware, better kept in mind with proper understanding. With this, we come to an end of the session. In this session, we focused on different biasing circuits, their advantages and disadvantages, along with their ability to provide stability. We also considered the definitions of stability factors, S, S prime, S double prime. Hope this session is useful to you. Again, we meet soon in another session with a new topic.